Welcome to another video. This time I want to start off a new maybe series, and maybe this is similar to previous videos but also a bit different, because this time I want to dive deeper into the ZCash technology with zero knowledge proofs and everything. And the main reason I'm doing these videos now is that I want to dive deeper into that technology myself, get a better understanding of all that things. And the best way to really understand something and to truly understand it is to try to teach it and explain it to someone else. So that's why I'm doing this video. If anyone gets any value out of that, that's great, that's awesome. But honestly speaking, you are my rubber duck to just so I can explain the stuff into the void so I get a better understanding. But feel free to come for a ride. What will this be about? Generally, I called it ZCash Zimplified because play with words is fun. The agenda for the next videos is roughly this. That's the agenda because that's how far I am right now in my own research, and whatever comes after that we will see. If someone has some ideas or questions about it, or says please do this topic in the context of the ZCash technology, feel free to leave a comment. I will read them. I will most likely react. But yeah, let's see where this leads us. Also, if someone else is diving into this topic and wants to connect, wants to share progress and talk about it, please reach out. I'm always looking forward to other builders and tech people that I can share ideas and topics with and talk about that stuff, because there are not that many people you can talk on that level about it, because not that many people are interested on that level. Regarding the level, generally I don't plan to do a complete top level how to use it or anything. This is also not about price or anything. It's really about how this thing works, how zero knowledge proofs work, and how they actually work in the ZCash content. That being said, yes, I won't do just total top level, but the plan is that anyone without any prior knowledge, so if you have zero knowledge about zero knowledge, you can still get it, all right? So to build the whole thing from the ground up, also the goal is that you don't need a math degree or anything for it. It would help. It would definitely help to have an interest for that stuff. But I want to try to make it in such a way that even if you just have a general idea and interest in it, you gain more knowledge and overview on that level. And if you have a deeper interest in it, you gain deeper insights in it. So I will try to cover and explain how it actually works, but also on a level that helps understand it without the deeper insights. With that being said, it's a lot of intro, but today let's start with the general shield transactions and what is a Merkle Tree, because I didn't know what else to put the Merkle Tree in. And then we will go in later videos about the general intuition about zero. What is zero knowledge? We also will touch it a bit today, but yeah, it needs a separate video. Then we go a bit more into the elliptic curve stuff, which gets a bit more math heavy, and then the actual snarks and what's needed for them. A bit of a disclaimer, so to speak. This is my own research. Assume that I'm wrong. I can't guarantee that any of that is actually true. It's my best knowledge right now. I'm learning with every new topic and every new question. I realize or understand better everything else. Maybe I will do another series of videos once I'm done with those and redo them with all the things that I know better then, but we will see. The goal is, as I said, a good overview, intuition, not 100% correctness in the details. Yes, I want to get to the how it actually works, so I want to go into the details, but I won't do a math paper here, because if you read the ZCash protocol definition, it's over 200 pages of real math paper. So yeah, heavy stuff, and to get all the details 100% correct, formally verified there, that's I would lose even the last few, and that's also not the goal. The goal is to have a correct intuition and overview and understanding of how it works, not every last index and semantic correctly. Also, a bit of a warning, it will sometimes get math heavy, so there is some stuff that's really math focused. I will try to, as I said, not have it completely on the math, and there will be sections in the videos where we dive into a more heavy math, but I will tell you what those areas will be, and it should then always be possible to skip the session or this section and continue with the other parts. And of course, as always, this is no financial advice, but I mean, it's just the tech behind it. It's pure education. So I hope no one even thinks about taking this as financial advice. Always do your own research and make your own decisions. Good. With that, let's start in. Today, general ZCash, what's the idea and of a shielded transaction, and then we go a bit into the Merkle Tree. To go into the shielded transactions, maybe a quick rough what is ZCash? ZCash is a cryptocurrency, pretty from the idea has similar to Bitcoin. It's also been here for many years already. It's proof of work. It has the same supply cap as Bitcoin, so very similar in that regard. But the main difference and the main idea is with Bitcoin, everyone sees what's happening. So if there's a transaction, everyone who monitors the chain sees what address sent which funds, what amount to what other address. ZCash wants to change that, or wanted to change that and changes that to say you can have shielded transactions. So you have both. You have transparent transactions where it's the same as in Bitcoin, and you have shielded transactions where the transaction happens, the value transfer happens, but when you have a shielded transactions, only the people who have the viewing keys, so the keys that for the addresses that are involved in that transaction, can see what actually happens there. And for everyone else, they only see that there was a transaction and it paid that amount of fee. They don't see anything, who paid it, the amount, or anything. So that's the overall topic about ZCash, and that's what we want to see. And how they do it is with this zero knowledge. If someone asks why did Bitcoin not do it like that, that's because this technology was not there when Bitcoin was invented. Satoshi wanted to do it. He had it on the mailing list that it would be great to have that privacy. But yeah, back then, zero knowledge proofs were not discovered, because they always say big, great things discovered. So let's see into the details. So ZCash transactions. A ZCash transaction, I think I should scroll a bit, zoom in here, better, yeah. In general, ZCash transactions look from the idea, pretty similar to Bitcoin transactions. In Bitcoin, if you don't know, I have a video about UTXOs, you can look it up. In Bitcoin, you have the UTXOs that get spent. In ZCash, they call them nodes. So a node is an unspent transaction output, so to speak, in ZCash. So the outputs of transactions that define what value is transferred to what receiver. So what address? And every node in ZCash contains a receiver, a value, and a randomness. Those two are the same as in Bitcoin. Every output has a how much is paid to that output and what address or what script is it paid to. ZCash adds the randomness, which is necessary for this zero knowledge topic. But for now, we can ignore it. One important thing to note, because we will need that in a second, is that cryptographically there is a lot of stuff happening behind the scenes there, which we will go into in the other videos. But what you need to know is from those three things in the node, because that's what defines the node, you can derive a so-called node commitment, we call it NCM, which is derived just from those values without need to know the private key. So you don't need to know the keys or anything. It's just, that's the node commitment. And you have a nullifier, which needs the private key of the receiver. So if you have the private key of this receiver address, you can, from this node, create the nullifier. Very important to keep in mind is that you can get from those values to those things, to the node commitment and the nullifier, but if you have only the node commitment or only the nullifier, or even if you have both, if you have anything of that, you cannot, without the private key, you cannot go back to that. So you have no way of getting back to get those values out of that. Also, if you just see any node commitment and a nullifier, you have no way of knowing if those two belong to the same node. That's in the zero knowledge, but that's just for now to keep that in mind, because that's what we will now base our transaction data on. Now, how does such a transaction look like? This is now about the data that's in the transaction, not what's visible on the chain. It's not visible, but just to get an understanding of what's happening there. Because what's happening in the transaction is similar as with UTXOs in Bitcoin. You have the inputs. In this case, it's nodes, because ZCash is nodes. Node A with the receiver A, the value of A and the randomness of A, and the node B with receiver of B, value of B, and randomness of B. So in this, since they are now the input nodes, that's kind of the spender, but the node itself always has the receiver or owner of the node, if you want it. And then we have the output nodes, which is the outputs of the transaction, and node C with the receiver C, value C, and randomness C, and node D with the values. And there are a few things that must hold invariant for each transaction. And one is that the values need to match. VA plus VB needs to be equals to VC plus VD. So the amount that's going into the transaction needs to be exactly the amount that goes out. I'm ignoring the fees for now, so in real life this is plus the fee, but it's a bit easier to understand if you just ignore the fee for now. It doesn't matter, it doesn't change the equation a lot, so it's kind of the same. But that's the rough idea. You can't create coins out of thin air. You can only spend get out what you put into the transaction. There must be no double spend, so it must be made sure by the chain, by the consensus, that node A was not spent already and node B was not spent already. That's a double spend thing, that you can't double spend at the same amount. And it should be clear that only the owner of the private key for these receivers can use that node in a transaction. So if I'm the owner of the receiver A, no one but me, or only the person who knows the private key should be able to sign that transaction so that it's valid. Makes sense? Otherwise, the whole thing breaks down. So that's the data behind the transaction. For those who know Bitcoin, it's basically the same. Bitcoin has the same thing, but on Bitcoin you can verify all of that publicly because you see the values, so you can easily check the values. You know all UTXOs and all what is still a UTXO, so still unspent, and this must be true, and then therefore it's trivial to check them. The only thing is the signature of the transaction. It's cryptographically relevant, but that's the only thing. But you see everything else. Now with ZCash, zero knowledge, we want to hide most of the stuff. So what we show, or what's shown on the chain, the visible stuff, is on the one hand we get the nullifiers for a node. As I said before, nullifier can be derived from that, but only if you know the private key of the receiver. So to be able to provide the nullifier for a node means you have the private key for the node. Then you can provide the nullifier. So you get the nullifiers in, it's visible on the chain, and the node commitments for the output nodes are visible on the chain. As I said before, from the node commitment you can't know anything about it. Also from the nullifier you can't know anything about that. So you see that and you get a set of ZK snark proofs, zero knowledge snark proofs. That's what you see from a transaction on ZCash. So no information about what actually went in, you just see that there are nullifiers, and no information what get out. You only see that those are the node commitments that are the output nodes. What you can now transparently check, so without going into the zero knowledge, is that those nullifiers have never been used. Because you can just keep track of all nullifiers, or you have to keep track. So a ZCash node, let's say a ZCash system. The system takes care of basically storing all the already used nullifiers. Whenever a nullifier is used in an input, it stores them, and therefore you can easily check, have those nullifiers already been used. If they are already used, it would be a double spend and it's invalid. If they are not used yet, it's valid. And provided that those zero knowledge proofs are valid, because that's the nature of a zero knowledge proof, that you can verify that it's a valid proof without knowing what is proven. So, or you know the structure of what is proven, you know that this equation gets proven and stuff, but you don't see the actual values in there. And those zero knowledge proofs, that's the thing, they guarantee that those nullifiers and the nullifiers belong to an existing node commitment that has been an output previously on the chain, so that they are not made up out of thin air, but they belong to some already unspent node. They are the fact that they have not been used before makes sure that they are unspent, and the zero knowledge proof internally guarantees that they belong to an existing output node. And this happens via the Merkle root and the path in the Merkle tree. The thing is, the Merkle root is visible, the Merkle tree, the path in the Merkle tree not, because that would mean that you need to know which commitment it was. That's the thing. Zero knowledge proofs guarantees that they belong to an existing node commitment without telling anyone which node commitment it is. Then the zero knowledge proofs ensure that, or guarantee that this equation of the input and those values match, without revealing what's the actual values. They just verify and guarantee that this equation holds, but you have no idea from the outside what values are in there, and that only the owner of the receiver can create those proofs. So that's the signature part again, that it's only the owner can create the proofs for those input nodes. So you need to know the spending key. With that, you prove all those three things, because you have the double spend check with the nullifiers have not been used, and with the valid ZK proofs, you prove that they are already, they exist on the chain and have not been spent, that the value is a match, and that it's a valid signature. And to be able to do that, as I said before, what then happens on the chain from this transaction is that the used nullifiers get added to the nullifier set. So that's an ever-growing set of infinite up to a huge amount of nullifiers that have been already used, which is necessary to check against double spend. and the node commitments C and D are added to the Merkle tree and create a new Merkle root. And that would be it. So that's what's needed, and how zero knowledge or ZCash transactions shield the values inside. As I said, this is now just for the overall idea how this works, and how zero knowledge actually works we will do in the next video. This video I will just quickly cover one additional topic, the Merkle tree, because Merkle trees are also in Bitcoin used, but yeah, I'm not sure if a lot of people know what a Merkle tree actually is. It's quite simple if you have ever heard the data structure of trees. A tree, and in this case a binary tree, is a data structure where you have a root, and then you have two, every node in this structure has two children. And that goes down to children, to children, to children. And at the bottom layer, I mean, a tree would be the root in the bottom and the leaves on the top, but never mind. There you have those nodes at the end are called leaves. That's a tree, binary balanced tree. And if you now, the special thing about the Merkle tree is that you have values in each node, and the leaves start with a value. In this case, it's the hash of the node commitment A and the hash of the node commitment. So the leaves represent node commitments, so to speak. And we have always the hash of a value. And then the parent of two nodes takes the hash of the combination of those two values. So it's the hash of the combination of two hashes. And then another level up, it's again a hash. It's again a hash. So you have a lot of hashes, and this way up about those hashes is called the path in the Merkle tree. This is the Merkle root. And if you now want to say this value is in the Merkle tree, you can provide the hash path to this level, because you can say, okay, this is my hash, and this is the path up in the root up to this root. And if you are able to prove that you say you have a path that comes to this root, you have proven that this thing is in the tree, if the other root is the same, because you cannot get to this root, or that's, you need to use a hash function that has no collisions and everything. But if you have that, it's impossible to get to the same root if it's not in the tree. And that's a Merkle tree. And in our case, in ZCash, we use a Merkle tree of node commitments. So the leaves are node commitments, and then you hash that, hash it, hash the combination, hash the combination, hash the combination. So you come to a path through the root, through the tree to the root. And in the transaction, if now node commitments gets added to the tree, they get added on the leaves, which makes a new, changes the root and changes everything above them. So if here we have now a new leaf node, it goes up and changes everything. In the actual implementation, it's, as far as I know, it's not that a node is actually added and the tree grows. It's that the full tree is already initialized, but the leaves that are not used yet are initialized with 0 values. So a clear not occupied value. So it's an existing tree getting filled with values, and the values change, and not a tree growing. But that's more of a detail. Yes, so that's a Merkle tree, and that's how shielded transactions work, or what's the idea behind shielded transactions in ZCash. 25 minutes, good time. If there are questions, leave a comment. Also, even if there's anyone watching that and wants to see more, I'm happy to hear about it, because yeah, as I said, so far I'm doing it just for myself, but let's see. With that, see you in the next video.